And so we calculated what pressure 1 and pressure 2 would be, right? And I want to emphasize these equations have nothing to do with volume, right? And the pressure is solely determined by the forces that the gas feels on it, okay? In any case, in our sort of kind of hypothetical way that we split up this expansion, initially all we're doing at the beginning is just looking at the changes in the pressure while volume stays the same, okay? And we can kind of visualize this step by revisiting that pressure versus volume graph that we looked at the beginning. Okay? All right, and so in this pressure volume graph, what we're doing is we're starting at state 1, and then what we're doing is all we're doing is staying at the same volume, but we're lowering the pressure of our system down to pressure 2. Okay, so that's what we're doing. All right, and then after we lower the pressure, what we're going to do is we're going to stay at that same pressure, and we're just going to expand the system to volume 2. All right. Okay? And so for step 2, to move that piston, the gas needs to exert a force, F gas, that's equal to the force that's now acting down on it. And so once we remove that block, the only two forces acting on the gas are the atmospheric pressure and the weight of the piston. Okay? And so the forces that the gas must act against are just PATM AP plus mass of the piston times gravitational acceleration. But as we saw with our earlier force balances, we know that that's just equal to P2 times the area of the piston. Okay? And so if we calculate the work that's exerted in the second step, we know that in general, work can be calculated as force of the system, or the gas in our case, force of the gas times the displacement, and the integral of that from position 1 to position 2. From our force balance, we know that the force that the gas is acting against is equal to this, P2 AP dx. Now we know that the area of the piston is a constant, and we can move AP inside this differential here so that we get area times displacement, which gives us a volume. But what we also need to remember is that the way we're analyzing this expansion, for the work, we're only looking at the gas changing its volume at a constant pressure P2. And so that means in our work calculation here, the pressure, too, is also going to be a constant. Okay? And so what we could do here is we could pull the pressure outside of that integral. We get area times displacement, which we could then turn into a volume. And if we go through that integral, what we get is then, now it's just pressure times V2 minus V1. Okay? And so you could see this is different than the results that we got when the expansion was very slow and the pressure could be described by the ideal gas law. All right? And so we'll sort of revisit that case later on. But what we see now is that the work exerted by the process is just pressure times the differences in volume. Okay? And once again, we could illustrate that on our PV diagram as well, right? And so the work is just P times the change in V, and that's essentially the area underneath the curve here. Okay? Right? And so the work that the system exerts during that expansion is just equal to this area. Right? It's not equal to the entire area underneath the curve here. Right? And so what we could see already is that the work we get from this rapid expansion is less than the work we got when we had that quasi-static isothermal expansion. Okay? All right, so that's one thing I wanted to highlight. The other thing I want to talk about is, we had the process that we studied occurred in the case where we were going from volume 1 to volume 2. But let's say after we expand the gas, what if we wanted to move the system back to V1 and pressure 1 by putting the 1 kilogram block back on it. Okay? All right, in that case, can split up the backward process the same way we split up the forward process. Okay? All right, and so the way we split this up is as soon as you put the block back on the piston, what you would then, the way you could model the system is you would say system goes from P2 back to P1, and the volume stays the same. And then after you change the pressure, then you would change the volume. Well, system is at P1. Okay? All right, and so based on that idea, as gas is going from V2 back to V1, the force that the gas feels is going to be equal to pressure 1 times the area of the piston, right? And so that's following in the same arguments that we did before. And what I want to emphasize here is the reason that we have pressure 1 here now is as soon as you put the block back on the piston, that changes the pressure that the gas is now feeling. Okay, it immediately jumps back up to P1. Right? And so if the work we calculated previously was the forward work, so work forward was equal to this, we could also calculate the work required of the backwards case. Okay? Or I'll just call it back. So that work backwards is going to be F gas as we go from X2 to X1. We could plug in the new F gas. So it's going to be P1 AP dx. As the volume is changing, both the area of the piston and pressure 1 are constant. And so we could pull out pressure 1. We now have the volumes in here. And what we get is P1 is V1 minus V2. Okay? Alright, and so in this case, we know V1 is less than V2. So inside the parentheses, we get a negative, right? But we also have this negative outside here. And that means we're going to get a positive work. Okay? And so if we draw this, if we go back to the graph that we had here, in the reverse case, or the backwards case, I mean, we start at state 2, and we end at state 1. But the way we split it up is we first go to pressure 1, and then we go to volume 1. Okay? And the work associated with the backwards case can be visualized as the area underneath this new red curve. Okay? And the reason I drew it like this is I want to point out that the area underneath this red curve is much larger than the area underneath the blue curve. Okay? And so mathematically we could describe it like this. The magnitude of the work forward, so if we're even just ignoring all the signs, is pressure 2 times V2 minus V1. The work backwards is equal to pressure 1, and once again ignoring signs, is pressure 1 times V2 minus V1. And we know that pressure 1 is greater than pressure 2, and so that means that the work backwards, the magnitude of it, is greater than the work forwards. Alright, and so we did all this math, but what does this all mean? And so essentially what this means is that more energy is needed to compress the system from state 2 to state 1 than is expended when you go from state 1 to state 2. Okay? And so, if you initially do the forward process, and the work exerted by the forward process, that's negative, because this is going to the surroundings. Okay? And so in the forward process, the system is giving the surroundings this much energy. Okay? But if you want to go backwards and go back to pressure 1 and volume 1, the surroundings not only have to give the system this much energy, but the surroundings also need to pay an extra amount of energy as well. Okay? And so we can think of that as extra energy penalty. And that has to come from the surroundings. Okay? And so, with that idea in place, I now want to define two terms for you. All right? And so, when we talk about processes, we can refer to a process as an irreversible process or a reversible process. All right? And so, for an irreversible process, the magnitude of the work going in the forward direction is not going to be equal to the magnitude of the work in the backwards direction. In the opposite case, for a reversible process, the magnitude of the work in the forward case is equal to the magnitude of the work in the backwards case.